Hi, welcome to Direct DC Circuits Part 2. We are going to talk about resistors in series and in parallel connections. Alright, let's start here. Okay, so first thing first, we're going to revise some of the concepts that we have learned at secondary school, and then we also want to add on with a bit more detail in terms of the theory, how we get the equations. So we're going to first look at resistors in series. So in this case here, right, remember in a series connection, my current is the same throughout. The same current flows through both resistors R1 and R2. Alright, and each of them has the same potential drop. We'll see more of that soon. Okay, so this is what we say. Since there's only one path through both resistors, current through each resistor is the same. Okay, so we have learned in the first part, conservation of energy, power generated by source is equal to the total power dissipated by resistors. So whatever power that is generated from this source E is equal to the total power dissipated across each of the resistor R1 and R2. Okay, so we can write EI equals to V1I plus V2I because power is just potential difference multiplied by your current, right? Then since I is the same, we can strike off the I, so we get E equals to V1 plus V2. So this is a convenient formula that this is similar to our Kirchhoff's second law, the conservation of energy. You have your whatever potential, whatever EMF is present is equal to the total potential drop across the resistors. Okay, then you have, so going back to this E equals to V1 plus V2, and then we can sub in terms of current and resistance. So I is equals to R effective. R effective is the overall resistance of these two resistors here. V1, which is the potential drop across R1, is equals to IR1, and same for V2 equals to IR2. So we write it down, IR effective equals to IR1 plus IR2. And you know what's going to come next? We're going to cancel away our current. And we get R effective equals to R1 plus R2. Okay, so this is for a series connection, series resistor. So you can basically chain it such that you have R1, R2, R3, R4, and so on and so forth. As long as they're all in series, you can add them up directly. So quite straightforward here, nothing new. Besides the proofing, I think nothing new that you have not learned before. Okay, next we're going to move on to resistors in parallel now. Okay, so parallel circuit is this way. You have your single EMF source coming out with a current. The current is going to split into two I1, I2. They'll flow into R1 and flow through R1 and R2 respectively before recombining to form the original current I, and then going back into your EMF source. Okay, of course the potential drop V1 and V2 are there. Right. So first thing first, so PD across each resistor V1 V2 are the same. This one I learned before, because if you look carefully, right, I'm just going to trace with I'm going to use a pen to draw. The first loop is this way, right? So this is the first loop. Okay, this is the first loop. Okay, so I can say that E is equals to V1. Okay, the second loop is like this, the second branch. Okay, it's just like that. Second loop is this way. All right. So this will tell you that E is equals to V2. Okay, so they both have the same potential difference. Okay, and both of them are equals to E. Right. So again, by conservation of energy, power generated by source is equals to total power dissipated by resistors. I can say EI equals to V1I1 plus V2I2. So potential power dissipated, power generated by this source, E times the total current I, is equal to the power dissipated across R1, which is V1I1, and power dissipated across R2, which is V2I2. Okay, from there we're going to go on a little bit more. So since V is the same, we can say that E is equals to V1 plus V2, and we're just going to write as V, right? So and total current is I1 plus I2. That's what we know. Okay, so then we're going to write the equation in terms of using my Ohm's law, using my definition of resistance, right? So if I equals to V over R effective, but it should be E. This one should be E, right? So we can I'll just go write a subscript E above for you, so know what's coming. This is V1, and then this is V2. Okay, so basically we just sub all as V lah. Okay, so then we can just use this formula, and then sub each of this into this formula here. Okay, so if V effective equals to V over R1 plus V over R2, and of course you can cancel the V, you get 1 over R effective equals to 1 over R1 plus 1 over R2. So again, if you have multiple resistors in parallel, you can just combine, you can add more of this, plus 1 over R3 plus 1 over R4 and so on and so forth. Right? Okay, so let's look at example 1 quickly. Okay, example 1, we have set up like this. We have uh, P to Q, but there are two branches across it. Alright, so there's this branch here which have two resistors in series, the 10 ohm resistor, 10 ohm fixed resistor, together with a variable resistor that ranges from 0 ohm to 1 times 10 power 7 ohms. Okay, and then the other branch has a fixed resistor of 1 times 10 power 4 ohms. Okay, so determine the range of effective resistance between points P and Q. So for this one, this R can be adjusted from 0 to 1 times 10 power 7 ohms. Okay, so we see what we can do here. So first thing first, we set this R as 0 ohms first. Then what we need to do is to add these two resistors in series first. Okay, add these two in series over here. These two must be added in series. Alright. Okay, then once I've done that, okay, so in series, so this will be 1 over 10, because it's 1 over 10 plus 0. Okay, so this is 10 plus 0, then inverse it, plus the inverse of the bottom resistor in parallel, 1 times 10 power 4. And then you get this to be equals 1 R effective. Then you inverse it back, you get R effective to be 9.99 ohms. Okay, and if now R is 1 times 10 power 7, my top branch will have a resistance of 10 plus 1 times 10 power 7. Then to find the parallel branches resistance, I inverse both sides, and then let it be equals to 1 R effective, and you get 9990 ohms. Okay, I don't know if you realize it or not. Okay, the range is this one, 9.99 ohms to 9990 ohms. But that's for the first one, right? 9.99 ohms, right? This resistance, the effective resistance, right, must be smaller than the resistance, than the branch with the smallest resistance. So for the first case, right, where it's 0, right, the branch with the smallest resistance is the top when it's just 10 ohms compared to 1 times 10 power 4 ohms. So the final answer must be less than the 10 ohms. Okay, and the next one, right now we have basically 1 times 10 power 7, 1 times 10 power 4. So the answer must be less than 1 times 10 power 4, which is, in this case, we got 9990 ohms, which is less than 1 times 10 power 4. Right? So this is something that you need to take note of. So if when you do a calculation for parallel branches, you get an answer that is bigger than one of the branch resistance, you know that somewhere you have made a mistake. Alright? Okay, example 2. This one is quite interesting. We have this setup here. Determine the effective resistance between A's and B, given that the resistance of each resistor is 2.0 ohms. So each of them are 2.0 ohms. So the key here is, how do you start this question? Right, what you need to know is that since we are measuring between A and B, right, we can just imagine that there's a battery here. Alright, I think that's the easiest way to think of it. There's a cell here. Okay, so you are measuring the potential difference across A and B. Right, but of course A and B is in, you can see that this is in series with this, and then this is probably in parallel, and then you get a bit confused here, right? So we need to have some strategy when we are doing this. Okay, so let's just talk about what you can do. The trick is to always start from the furthest branch from where you want to measure your PD. So I want to measure from measure across AB, right? I will want to look at the furthest away from it. In this case, I'm looking at this area. Okay, to help guide us in this discussion, right? I'm going to number the resistors here. So these are numbers 1, 2, 3, 4, 5. Okay, this is not the value, just numbering. Resistor 1, resistor 2, resistor 3, 4, 5. Okay, so let's see what I can do. Remember, we're supposed to start from the furthest. So we are going to start from furthest. We can combine 4 and 5 in series. Okay, if you look at this path between C and D, right, there are two paths. One path is down here. The other one is over here. Okay, I'm just going to use pen to draw for you so it's clear. So one path is this way. Okay, the other one is like this, right? Right? So we're going to combine these two. And then when we combine these two, we'll get it basically as a series circuit over here. Okay, 4 and 5 combines like that. Okay, now we can see that this between C and D now, it is two branches with a single resistor each, 3 and 4, 5. Okay, so you're going to combine these two in parallel. And once you combine in parallel, this is what you'll get. You basically have gotten rid of the last loop here. So this equivalent resistor, it consists of resistors 3, 4, and 5. Okay, so once you have this, you can combine. You can see that now across AB, there is one branch. There's one branch this way. There's another branch that goes this way. Alright, so now we can combine 2 and the effective resistance of 3, 4, and 5 in series. Alright, and then we form 1 mega resistor here, 2, 3, 4, 5. Okay, once you have that, you can basically combine in parallel, not series. Okay, I made a mistake here, so I should just rewrite this. So cancel this. I can't write parallel here, but I'm just going to do a double stroke so that you know that this is in parallel and not in series. Okay, right. So once we do that, we can look at how we go to do calculation. We go to start from the furthest loop away from AB. Okay, so first thing first, we find 1 over RCD. So this is your resistors. This 2 plus 2 refers to this one and this one. Add them in series first, then inverse and add to the inverse of this. Okay, then inverse back, you'll get RCD. That means from here to here, you're measuring these 3 resistors, right? The effective resistance is 1.33 ohms. Then once you've done that, you can combine this resistance with this one in series before combining these two in parallel with this. Okay, that's the next step. So 1 over 2 is this one over here, and this one 2 plus 1.33. Because this one here is 1.33, this is 2. Add them in series first, you get 3.33. Then inverse it, then you get this one. Okay. Yep, this is example 2a, right? So you get 1.2 ohms of effective resistance. Okay, so it's quite interesting this setup here. You basically using 5 resistors, but you get a value that's much smaller than your 2 ohms. Okay, so let's look at this one now. Okay, this one is a bit challenging, I would say. You have 3 resistors connected in a very funny way. If you trace the path, you can see that this point A is connected to the head of the first resistor and connected to between the tail of the second resistor and the head of the third resistor. Therefore, B is connected to the tail of the third resistor and the tail and the head of the first resistor and head of the second resistor. So we need to redraw this to make it easier for us to do, because this is very hard to interpret, right? So what we can do to guide ourselves when we redraw, right? We need to make sure that wherever we redraw, the connections still stay the same. So what if we do this in real life, right? We have a setup here. We have resistors actually connected and we have the cables connected, right? We are moving the parts around without changing any of the connections. That's the most important thing. Okay. But for diagram, right, we're going to just put some markers to help us know where we are looking at. So I'm going to give you some colored markers here. You have these 3 dots here. They are all attached to the tail of the resistors. That will help you to make sure that the connections are still correct. So like right now we can see that A is connected to the head of the first resistor, is connected to the tail of the second, because you can see the yellow one, and it's connected to the third resistor, the heads. Okay, so the rearrangement is quite interesting. It will look something like this. Okay, so how do we know this is correct? Because this looks much simpler compared to this, but we're just going to put in the dots for you over here. Okay, and we can trace the dots position. So let's look at A. A is connected to the head of the purple color resistor, which is here, and then connected to the tail of the yellow color one, which is here, and connected to the head of the blue color one, so that's here as well. Similarly for B, B is supposed to be connected to the tail of the purple, so tail of purple is here, connected to the head of yellow, which is here, connected to the head of the blue, tail of the blue. Okay, so that's here as well. So this one, now this becomes very, very easy to do. This is just 3 2 ohm resistors in parallel, and we can just add them up together like this. Okay, so the trick for this question is how you're going to redraw your circuit, right? Okay, next we look at example 3. Example 3 is a more application question that's linked to what you learned in COE when we talk about resistivity. Okay, so I'm not going to spend so much detail on the resistivity part. So I have a cable, 50 millimeter square cross sectional area. Okay, and then the length 120 meters. So you have one steel cable surrounded by 6 aluminum cables, all having the same dimensions. So you can quickly work out what is we can find R equals rho LA. We can find resistance of steel cable to be 0.216 ohms, and then resistance of the aluminum cable to be each 0.060 ohms. So all these are connected in parallel. Okay, so once we know that, we can basically just do a parallel connection for all 7 of these cables, right? So you get to find parallel cables, inverse of the steel plus inverse of the aluminium, but multiply by 6. Okay, so you note that I inverse first, then I multiply by the total number of cables. Alright, not the other way around. Does it make a difference? Yes, it does, right? Okay, so your final answer is 9.6 times 10 negative 3 ohms. Alright, so yep, so this is pretty straightforward as long as you know how to do resistivity calculation. Right, and you can see that this is in parallel. Okay. Okay, that's the end of this part. We will you can move on to complete the rest of this section before jumping on to the next part of the lecture.